Welcome to this session on time series forecasting. As part of SAP BTP AI best practices, we explore how to effectively identify patterns and data using SAP HANA machine learning tools. By the end of this session, you'll have a clear understanding of key principles, best practices, and implementation approaches to uncover the underlying patterns and historical data like trends, seasonality, and noise, and use these patterns to forecast future values. Our discussion will follow these 4 steps. First, we'll provide an overview of time series forecasting and its benefits. Second, we'll cover the essential prerequisites you need to have in place, including supported environments and required components. Third, we'll explore key choices and guidelines that impact your implementation, including model evaluation to understand how well a model is performing, therefore helping to identify areas for improvement and guide model selection. Finally, we'll dive into implementation approaches across programming models, providing concrete examples for Python and SQL. Time series forecasting is the process of using historical time-ordered data to predict future values. It involves identifying patterns like trends, seasonality, and cycles, and data collected at regular intervals. In the SAP ecosystem, this involves leveraging SAP HANA machine learning tools, specifically predictive analysis and HANA ML. The expected outcomes include the ability to predict future values based upon past observations, support to identify patterns like trends, seasonality, and cycles, and data collected at regular intervals, optimization of business processes, operations by enabling data-driven planning, and resource allocation. Why use SAP HANA machine learning for time series forecasting? There are 3 main benefits. First, algorithm interchangeability. You can easily switch between different algorithms like ARIMA, additive model, time series analysis, auto-exponential smoothing, Bayesian change point detection to best suit your specific needs. Second, out-of-the-box features that supercharge your development with built-in capabilities, data processing algorithms, seasonality tests, stationary tests, among many others. Third, security and SAP ecosystem integration. It's fully integrated into SAP technology, leveraging enterprise-grade security and native in-database processing. These advantages make time series forecasting more efficient and accessible for SAP users. Before implementing time series forecasting solutions, let's cover the necessary prerequisites. You'll need SAP HANA Platform 2.0, SPS 04 or higher, or preferably SAP HANA Cloud for easier management. SAP DataSphere or Express Edition can also be used for specific scenarios. Application Functional Library containing predictive analysis library and automated predictive library components. SQL script script server enabled for executing ML algorithms. To provide more context, SAP HANA is an in-memory database enabling real-time analytics and applications. The HANA ML libraries, predictive analysis library, and automated predictive library provide native in-database app functions for predictive analysis and machine learning. The script server is an auxiliary HANA process essential for executing these ML functions. Setting up these prerequisites establishes a strong foundation for implementing effective time series forecasting solutions at scale. Let's examine the high-level reference architecture for time series forecasting using HANA ML. The diagram shows the complete machine learning execution environment within the SAP HANA ecosystem. At the core is the SAP HANA database hosting, predictive analysis library, and automated predictive library. These provide the core time series forecasting algorithms. This architecture ensures efficiency, scalability, and secure time series forecasting while leveraging the performance advantages of an in-memory database processing. Effective data preparation is crucial for quality time series analysis. In SAP HANA ML, key guidelines focus on 3 strategic areas. First, consistent time intervals. Time series model benefits greatly from evenly spaced data points. Check for and correct any missing timestamps or irregular intervals using techniques like interpolation or backfilling. Second, resampling. You may need to resample or aggregate the data depending upon the desired forecasting granularity. For example, daily, weekly, and so on. Third, stationary. Many models, for example, autoregressive integrated moving, average assumed stationary, and others apply transformations like differencing or log transformations of the statistical properties of your series change over time. Other than this, handling null values and outliers is also important. Many SAP HANA predictive analysis library functions may abort in the presence of null values. Nulls can be replaced with default values using SQL or employee imputation techniques. Outliers can distort analysis and model accuracy. Identify and handle them using techniques like capping, smoothing, or replacing them with interpolated values. SAP HANA Predictive Analysis Library offers a wide range of time series forecasting algorithms. Choosing the right time series forecasting model and SAP HANA Predictive Analysis Library depends upon several key factors related to both the characteristics of your data and the business problem you're trying to address. Some of the commonly used algorithms are as follows. First, the additive model time series analysis uses an additive model to forecast time series data. It handles data with strong seasonal effects and is robust to change in historic trends. 2 ARIMA autoregression integrated moving average algorithm in SAP HANA Predictive Analysis Library is a powerful statistical method used for forecasting univariative time series data. Third, the Bayesian change point detection is a time series analysis technique used to detect points where the statistical properties of the data change, such as shifts and mean or variance. Fourth, auto-exponential smoothing automatically calculates optimal parameters for single, double, or triple exponent smoothing models. It forecasts based upon these parameters by exploring the full parameter space and evaluating quality using MSE or MATE. Comparing historical and forecast values. 5. Massive data parallel segmented time series forecasting independently applied predictive analysis library functions to subsets of data identified by a grouping column and a single cell, invoking massive data parallel machine learning processing. 6. The auto machine learning for time series. AutoML framework implementation greatly helps users in probing multiple algorithms and parameter variations for a given scenario. For selecting the best possible algorithm and model, let's discuss key choices that impact the performance of your time series forecasting scenarios. Model performance metrics are crucial for evaluating and comparing the effectiveness of machine learning models. They provide a quantitative measure of how well a model is performing, helping to identify areas for improvement and guide model selection. Common metrics specific to time series forecasting tasks are the following expected mean absolute percentage error. The expected mean absolute percentage error evaluates the prediction error of a forecasting model over the forecast horizon. It is the calculated of the mean of the absolute differences between actual and forecasted values, expressed as a percentage of the actual values. The lower the mean absolute percentage error, the better the model expected mean absolute error. The expected mean absolute error evaluates the prediction error of a forecasting model over the forecast horizon. It is calculated as the mean of the absolute differences between actual and forecasted values expressed in the same unit as the actual values. A lower mean absolute error indicates better model performance, and an expected mean absolute error of 0 signifies a perfect forecast expected mean absolute scaled error. The expected mean absolute scaled error is the evaluation of the error made when using the predictive model to estimate the future values of the target, whatever the horizon. The lower the mean absolute scaled error, the better the model performance. Expected root mean squared error is the expected root mean squared error evaluates the prediction error of a forecasting model over the forecast horizon. It is calculated as the square root of the mean of the square difference between actual and forecasted values expressed in the same unit as the actual values. A lower root mean squared error indicates better model performance, with a value of 0 representing a perfect forecast. Expected R squared. The expected R squared evaluates the proportion of variation in the target variable that is explained by the predictive model over the forecast horizon. It measures how well the model captures the variability of the data, with a value of 1 indicating a perfect explanation of the variation. However, R squared does not measure the accuracy or the goodness of fit. A model can have a high R squared while still being imprecise in predicting actual values. Let's discuss implementation guidelines for selecting your programming model. For data science workflows, we recommend using Python, with the HANA ML library providing a streamlined, intuitive experience aligned with standard data science practices, including convenient data manipulation and integration with machine learning workflows. For alternative approaches, consider SQL script to directly call predictive analysis library procedures when tight integration with SAP HANA artifacts is needed now. Let's explore the specific implementation options for each programming model. For Python developers, the HANA ML library is recommended for interacting with SAP HANA Predictive Analysis Library and the automated predictive library algorithms. Reference code includes SAP BTP AI best practices sample code and SAP community blog post, like a multi-valued time series modeling and forecasting guide with Python machine learning client for SAP HANA. For SQL developers, direct invocation of predicate and predictive analysis library procedures through SQL script is available. When embedding logic within SAP HANA artifacts is a priority, reference documentation includes comprehensive guides for these diverse algorithms. Each approach provides full access to time series forecasting capabilities while allowing you to work in your preferred environment. This Python example demonstrates implementing time series forecasting using the HANA ML library to call time series methods directly in the SAP HANA Cloud Predictive Analysis Library environment. This best practice guide reflects the collective expertise of data science and analytics specialists from across SAP, bringing together insights to support your time series forecasting. Thank you for watching this session on time series forecasting using SAP HANA ML. We hope the information provided helps you successfully implement effective capabilities in your business applications.